All right, so I was flipping through a maths sort of puzzle book, and this one caught my eye, so I thought I'd make a video about it. Here's the puzzle. The cubes of three consecutive numbers, 1, 2, and 3, are 1, 8, and 27, which add up to 36. And 36 happens to be a perfect square because it's 6 squared. Now the question is, what are the next three consecutive numbers whose cubes sum to a perfect square? So I'll give you 5 seconds to pause and think about that. Yeah, I thought it was an interesting question, and we'll jump into a solution. Here's just sort of the idea of what we're getting at, right? So 1 cubed plus 2 cubed plus 3 cubed is 1 plus 8 plus 27 is 36 is 6 squared. So basically our job is to find the next sequence of three consecutive numbers that give us a square number. Yeah, so let's jump into it and think about how we might attack this problem. First thing we could say is we could probably build a formula, couldn't we? Because we could say that if we let the middle number be n, if we let the middle number be n, then the three consecutive integers are obviously the one before n is n minus 1, and then we've got n itself, and we've got n plus 1. And then if you're summing those together, you get n minus 1 cubed plus n plus 1 cubed. And you know, this part's annoying, but if you expand n minus 1 cubed, you get this expansion here. And then plus n cubed plus n plus 1 cubed all expanded out. Then you collect some like terms. It actually simplifies very nicely to 3n cubed plus 6n. And then if you factor out 3n, you're left with 3n multiplied by n squared plus 2. So isn't that interesting? So we're starting to build a formula for how we might go about this. You know, this is our key formula. We need 3n multiplied by n squared plus 2 to equal m squared for some integer m. Okay, because it has to be a square number. So we can say that that has to equal some m squared for some integer m. Remember, integer's whole number, right? All right. So this is the most important part of our story, I think. And just recall that for any square number, I spoke about this in a previous video, but any square number, its prime factorization, so when you decompose it into its primes, gives you even powers of those prime factors. And it sort of has to make sense because the factor tree, if you draw it out, has to be symmetrical for square numbers. So let's just look at 36. If we break it down into its prime factors, we get it. It's the same thing as 2 squared times 3 squared, which is obviously 4 times 9, which is 36. But if we look at a different example, like 72, 72 is not a square number, and you can see that its prime factorization is not, does not have even powers. We've got a 2 cubed there by 3 squared. So 2 appears 3 times, which means that that's obviously odd. So a key fact that this is the crux of this problem. So we're going to just think about primes that are larger than 3. We'll deal with the primes of 2 and 3 in a moment, but let's think about primes that could be larger than 3. And then what could we say about that? Well, we know that 3 is not divisible by p. Okay, so 3 is not divisible by p because the only prime that goes into 3 is 3 itself, and we know that we're thinking about primes bigger than 3, so we're just going to say p greater than 3. So that's our first thing. All right, and this is the tricky part. So n and n squared plus 2, so from the previous formula, those are kind of like our factors, cannot both be divisible by p, because if p goes into n, then n squared plus 2 leaves a remainder of 2 when divided by p. And p does not go into 2 since we're talking about p greater than 2. In fact, we're talking about p greater than 3. But let's just break that down for a second. Like, let's just take n to be 4, okay? If n is 4, you know, you could draw, 4 dots. And then so n squared plus 2 would be 16 plus 2. But n goes into n squared nicely. It goes in n times. And then there's going to be plus 2. So there's always going to be a remainder of 2 when you divide n by p. So basically, the thing to take away from this is that n squared plus 2 and n cannot both be divisible by p. And I think that should make a bit of intuitive sense. So p must be a factor of exactly 1 of n or n squared plus 1. N squared plus 2 rather, never both. And never of the leading 3, because we know it can't be a factor of, p is not a factor of 3. Okay, So what that means is that one factor must therefore contain P an even number of times on its own with no help from anywhere else. And that's important because if we break this down into our sort of prime decomposition, let's look at the number 4 as if we were to break it up. All right, here's our factor tree for the number 4. So let's have a look. If we were just testing things, right? We were just testing 4 to see if 4 might work. 3, 4, 5, will that work? Well, let's check. We put 4 into here, so we get 12. 3 times 4 is 12, multiplied by 16 plus 2 is 18. So that gives you 216 apparently. Okay, you break that down into its factor tree. You've got the leading 3 that's always going to be sitting there. And then you've got 3 times 72 is 216. And then you've got 8 and 9. If you break 72 up, and then you've got 2 times 2 times 2, and then times 3 times 3. So we can see that the prime decomposition of 216 is 3 cubed times 2 cubed. So we've got odd powers. So that can't be a square number. And in fact, obviously, 216 is not a square number. So we've sort of excluded 4 now from our possible list. 4 can't be correct. And this is sort of a strategy we have to use as we go through. If we then look at n equals 24, so we've skipped quite a few, it actually works out. And so there's our answer. We're saying that it goes 24, so 23 cubed plus 24 cubed plus 25 cubed gives us 41616, which is 204 squared. In any case, we break it up, we get 41616. We've got that leading 3, and then it's 24 times 578. And this is the same thing as 2 cubed times 3 times 2 times 17 squared. And notice that that is our P, right? That's the prime we were interested in that was greater than 3. And so that's 17, and obviously appears an even number of times, which is what we wanted. So we can see that this interesting number, 41,616, has all even powers for its prime decomposition. So for n equals 24, the leading 3 combines with the 3 inside 24 to give 3 squared overall, which is even. The 2 cubed in 24 and 2 to the power of 1 in 578 combine to 2 to the power of 4, which is even. 17 squared comes entirely from 578, which is already even, which is sort of what we were saying, right? This 578 is this n squared plus 2. We knew that the prime greater than 3 had to come from either n squared plus 2 or n, and in this case it comes from n squared plus 2. So if we keep going from there, we're sort of just summarizing it from here, I think. Obviously we just need to search for solutions, which is sort of what we did. And here's just a little table showing it. 1, 2, skip a few, you get to 24, and then you obviously find a solution here. 204 squared is 23 cubed plus 24 cubed plus 25 cubed. And so, there you go. There's your solution. Isn't that interesting? Okay, I'll leave that there for you to read. It just basically goes through what we just spoke about, but hopefully it makes some sense to you as well. Make it make sense in your own way as well. I think that's important. And there you go. I don't know, just an interesting little problem. Trying to do some more interesting things, not just curriculum stuff. Sometimes that gets a bit dry after a while. So there you go. This was the algebraic identity 3n times n squared plus 2 equals m squared is the key. It turns an open-ended search into a structured number theory problem. There you go. So you can tell that AI sometimes writes a lot of this code. So if you're interested as well in that, let me know. I can show you how to code some of this stuff. Good luck with everything you're doing. Reach out if you have any questions, and I will see you soon.